So this is the square root Verilog code, okay, corresponding to the awesome chart. Okay, I have actually moved these local parameters. They were local parameters before. I moved them to be parameters that can be changed during instantiation, the scale as well as W, the width, the total width, and the number of iterations. All right, so these are now parameters. I didn't change anything in the ports of the module, okay? But I have a local parameter, which is basically one scale more than W, which just defines W plus scale, okay? W plus scale. All right, now my state, since I have only two states, it's just S0 and S1. And the state is just 1 bit in this case. All right, so these are the definitions for S and X. And this is the S by X. Okay, you can see in S by X, I used, because I have the number of bits for this. The number of bits is scale more equals scale more, okay? The way to create the zeros, number of zeros equal to scale more, is using the replication operator in Verilog. This is the replication. I'm replicating the bit 0 scale more times, okay? This creates a string of scale underscore more zeros and assigns it to S by X if this condition is not satisfied, okay? In fact, if we go back to the algorithm here, to the pseudocode, I mean awesome chart, I think, yeah, S by X also depends on ITE, okay? ITE being not equal to 0, okay? So I'm going to add this, to, I'm going to move this here because I need to use it. So state equals S1 and ITE does not equal 0. In this case, scale S by X is going to be this part here. Otherwise, it is 0. Okay. Here we need to define this as 8, which to avoid warnings. Okay, to avoid warnings, I just tell the compiler what is the width of this constant. Otherwise, it will be 32 by default. And here, yeah, we have the detection of positive edge logic here. Okay, and we have ready. Okay, ready is equal to S, state equals S1, and ITE equals 0. This is the case, then ready is going to be 1. Otherwise, ready will be 0. D out is going to be equal to X if ITE is 0 and state is 1, as in the awesome chart. All right. Otherwise, it is all zeros. Okay. Now, this is the reset logic. We go to S0. In S0, we check the positive edge and go. This is the case we prepare our variables and then move to state S1. Otherwise, we stay in S0. Okay. In S1, we check if ITE does not equal 0. If this is the case, then this is where we update X and ITE, decremented. Otherwise, if ITE is 0, then we just need to go to the next state based on positive edge on go. It's to S0 if we get a positive edge on go. This is like a handshake. We received the value. If we don't receive a positive edge on go, we will stay here until the user sends a positive edge on go. All right. And here we have a default, although it's not required because we enumerated all the cases, but it is always recommended that you add the default case. Maybe later I change my algorithm and add some more states. And if I didn't include the default, I may forget to include it. Okay. So it's always a good practice. Even if you enumerated all the cases, just add a default case. Okay, for the case in which the machine is powered up. Okay. Right. So this actually covers the algorithm here. Okay, the square root itself. Now the test bench. Okay, the only difference here is that we are instantiating with the parameters. We are passing the parameters, and I'm defining local parameters, scale and width, and these, and then I'm passing the scale, width, and IT. Actually, I don't think this is needed in the test bench, so I can remove it. Okay, I can remove it. Okay, so now we would like to do like what we call a test, a real test. Okay, I want to generate the square, a table of square roots of numbers starting from 2 all the way to, let's say, 31 or something like that. Okay, any number, and then compare with the square root calculated by, let's say, the calculator or the system task here, system task, which computes the square root as accurate as possible using floating point. Okay, so for this I'm going to create variables here. Okay, real variables, which is basically single precision, I believe. Real is when you use floating point numbers in Verilog, but it's only used for simulation purposes. It's not used for synthesis. If you want to use synthesis, then you need to actually have more work, and you need to actually implement the floating point unit. Tamim. Tamim, can you write your question, because I can't hear anything from what you said? Please write your question on the chat, and I'll read it and then answer it. So let me say that my SQ will be the value of the square root received from the circuit, and I have GSQ, which is the golden square root as calculated by the system task, and I want to calculate the error. Okay, the error, which is the difference or the absolute difference between the square root and the golden square root. Okay, and I want to use an integer I for a loop. Okay, I want to do a loop. All right. Okay, so now what I can do is basically okay, let's do it here. I can say for I is to I less than, let's say, I don't know, maybe let's have it until 17 or 18. Okay, I equal I. You cannot say I plus plus, by the way. Here it's not a Verilog syntax. This is Verilog syntax. I plus 1. And you have a begin. And somewhere at the end here, we have maybe here, yeah. End. Okay, this is for the begin and end. So remember our circuit, what does it do? What does it do at the beginning? Our reset, the reset operation is outside. I'm going to do it outside the loop. Is okay. And then let's have, for example, a negative edge before entering the loop, just for the sake of making sure that you took your time for resetting, okay? And then, okay, in the loop, I need to provide a positive edge on go, okay? So now we are in state S0. So I need to say here, okay, I need to say, let's see the question from Tamim. Is synthesis real? La, no. Real is not synthesizable, Tamim, okay? It's just simulation. I said that. I just said that explicitly, okay? Real is just for simulation. Okay, Tamim? You can use interactions, by the way. You can use it. Okay, great. So here we have to say go 0 and prepare the n, data n, to be I scaled by or shifted to the left by scale. Okay. And then in my next negative edge, I can say go equal 1. This is a positive edge on go. Yeah. And then wait for the positive edge ready. Yeah. And then give it 100 time unit. And then loop back. Okay. Loop back for another positive edge. Actually, I need a positive edge in order to restart. I need a positive edge on go. Yeah. So after this 100, I will just say, so you remember, Shabab, in the algorithm or ASM chart, I need once ready is 1, I can't go back to S0 unless I have a positive edge on go. Okay, so I need a positive edge on go. Okay, this is why I'm giving a positive edge on go here. To go back to S0 and then restart the calculation using another number. Okay, the next I. All right, and then I finish. Okay, here, once you have a positive edge already, I know that my SQ, I can read it, right? Which equals what? Equals D out, yeah? D out. SQ is equal to D out, however, divided by how much? Let's say 1.0 multiplied by 2 to the scale. Okay? 2 to the scale. Why did I say 1.0 here?
To make it float.
Yeah, exactly. Yes. And also, I can calculate the golden, the one that I know for sure it is correct. The golden square root is equal to square root This is just for simulation. It's given to you as a system task, okay? System task. Square root of I, yeah? Square root of I. And my error is going to be what? It's the absolute value of square root minus GSQ. Now I can say display and give it like SQ equals %0F and GSQ equals %0F and error equals %0F. Okay? And then give it SQ, GSQ, and error. I think this is it, right? Right. I'm going to stop this video and then start another video for the simulation, okay, simulation part of this test bench.